one time. How's everyone feeling today? All right, so today we're actually working on lesson 11. How can the acceleration and tension be calculated for two masses connected by a string when there is a friction force? This is just like lesson 6, but this time we're including the friction force. So on Monday, we're going to do the the shoe lab, and then have our homework discussion, and then we have the big test on Tuesday. Ladies and gentlemen, I want to make an announcement about this exam. This exam, the questions are going to be straightforward. All of them you would have seen before, either on a homework problem or a test your understanding question, or from the review sheet. So basically, since it's material you should be able to do, and there's not going to be any like new punches or below the belt shots or anything like that. Basically, what I'm trying to tell you is the test on Tuesday is definitely not going to have a compression.
Oh God.
Okay, so if you do your work, you should be fine. So just putting that out there.
Even if like the entire class
You're saying we shouldn't do.
Honestly, I'd rather take the hard test with
What if the average is like a
Ladies and gentlemen,
It's more realistic this way.
basically, folks, it's like this is what you should be able to do, and if you don't perform at that, then basically I don't think you're putting in the work needed, to get that score. Okay. So with that said, folks, we're going to be doing lesson 11 right now. So for homework, of course, you have lesson 11 homework, which is this problem over here, page 132, number 93. If you have trouble with it, folks, notice it's linked. You click on it, you can hear a solution there. And then the rest of that review sheet, we've done quite a bit of the review sheet, but there's some more to be done. And then I'm also going to be giving you a take-home quiz, which will be due on Monday. Due to the way the periods fell, we didn't have time to do in class. The other class did it as a in-class partner quiz. You guys are going to do it as a take-home quiz, and that'll be due on Monday. And then, of course, we'll have time to go over that as well on Monday. So that's the plan, Stan. Yes?
Do you have the question numbers like you did for the last unit? For the really big multiple choice review sheet, like those questions?
I don't, but if you want, I can look through that and I can add them. I could add them and put them here,
Please.
Okay. That's a good request. All right, so two-mass system with friction. Here we go.
So this is going to be on stuff after lesson 6.
Well, the thing is, the stuff after lesson 6 incorporates the first 6. So really, it's on the whole thing. Okay? Also, a lot of you did not hand in test corrections, so you really want to make sure you learn from the last test, because it would be embarrassing to get similar questions incorrect on the follow-up test. So make sure you have your test corrections in by Monday and Tuesday of next week as well. All right, so we're going to look at a sample problem here where we have an object
Can we get the questions later in class?
on the table here.
last year, I think our Southside sports team has won every single sport besides baseball.
Okay, come on, let's stay focused, folks. Will M1 stay or will it slide?
They didn't win.
If M1 stays, calculate the maximum static friction force, holding it there. If M1 goes, calculate the acceleration.
Mr. Sosinski?
Yes.
This would most likely be a part 2, right? Not a multiple choice?
Either or. Either or.
You're gonna have extra help on Monday, right?
Of course.
So like if we look at all the homework problems we should do left. I'm so worried about this. Why are you not happy about this? It is bad. Person right now. Kind of like yeah. On the last test. So basically we're being asked if the first mass will stay and if it does
That's what we've done so far.
how much friction force, if it goes
What are you
like
talking about this?
All right.
Come on, do this.
So, if it's going to stay, then we know that basically both objects will have an acceleration of 0. Therefore, both objects will have a net force acting on them of equal to 0. So, what we're going to have to do is analyze this object over here first. And if it has a mass of 5 kilograms, we know that its weight is going to be equal to m2 times g, which would be 5 kilograms times 10 meters per second squared. So that's going to be 50 newtons. But if it stayed, that means it's not rising or sinking or accelerating or anything. So this tension force due to that cable right there, how much would that tension force have to be if it stayed?
Equivalent to
50.
Yeah, so it would be equal to 50 newtons. But I'll have to put in parentheses here, if it stays. And we're not sure if it stays yet or not, but if it did, then we know however much this object here weighs, 50 newtons, well, then that cord here is going to have to be holding up 50 newtons. And since that cord is all part of the same cord right through here, if it's pulling back on this object 50 newtons, Newton's third law says, how much would it be pulling over here?
50 newtons.
So if it stays, that tension force over there would also be 50 newtons. Again, if it stays.
But if
So
it
what you have to
goes...
do is find the maximum friction force. If it's
Right.
Equal to or greater than 50. Then.
Exactly. So what we're going to have to do is just compare the rubbing together force, like right through here, and we're compare it to this 50 to see, is there enough static friction force available to keep it there? So we need to calculate this force going this way. And right now I'm just going to call it the force of friction because I'm not really sure yet if it's going to be a stay or go situation. But we're going to calculate the maximum static friction force to see what's going on here. So, looking over at this second object right here, or actually I'm calling it M1, we know that M1 has a weight force, Fg equals M1 times G. M1 is 10 kilograms. G is 10 meters per second squared. So Fg of the M1 mass is going to be 100 newtons. And since that object is not falling through the table, we know that the normal force holding it there is going to be equal to exactly as much as the weight force, 100 newtons.
Wait, if they cancel each other out, why would you need to know that?
Because you need it.
Well, it's
You need the normal for this formula.
Oh,
yeah, we need to know what that normal force is to calculate the maximum static friction force.
Okay, okay.
So now that we know the normal force and we know the mu sub s, knowing those two things now, we can calculate the maximum static friction force.
0.40 times 100 newtons.
Mu sub s times the normal force. So F s max is equal to 0.40 times 100 newtons. And what does that come out to be?
30.
40 newtons.
No.
So,
It's
do we have enough static
Yeah,
friction
it does.
force
It stays.
no, it goes.
to keep it there?
No, we don't.
Because if it stays, we know that this guy over here is going to be pulling down with a force of 50 newtons, so that upward cable force would have to be 50 newtons. So this force here to the right would be 50 newtons. So if this cable force to the right is 50 newtons, if it stays, to support this guy over here, we know that we would have to have how much static friction holding it this way? 50 newtons if it stays. But do we have enough? No. Because the most we could possibly get is 40 newtons. So since this tension force here is greater than the maximum static friction force,
Therefore,
then it goes. It slides.
it's live, baby.
Slide, baby, slide.
And then what was the question? If it slides, what did you have to calculate?
So,
We get to the acceleration.
will it stay or will it slide? So we now know it's going to slide. If it stays, calculate the maximum, or actually the static friction force. We don't have to do that because it's not going to stay. If it goes, calculate the acceleration.
Oh yeah.
So that's what we have to do now. Calculate that acceleration.
So,
F net equals on that.
So, we're now going to calculate that acceleration. And of course, we're going to have to use the mu sub k because we established it's going to go. So, we now know that this Fg over here is 50 newtons. But since we know it's going to slide, is this tension force going to be 50 newtons?
It's not.
No. Is it going to be more or less?
more.
Less. No.
More.
The tension is going to be less because you have to subtract. No, you have to subtract.
Since we know it goes,
Oh, I said plus. Now he wants me to change it.
this one here it's going to be going down.
Yeah.
Now it has to.
So how is that tension force up going to compare to the weight force down
Less.
if it goes down?
Less.
The tension force is going to be less.
Yeah.
So we don't know what it is, but all we know is that it's going to be less than 50 newtons. We do know that, but we don't know how much. And again, same cable, the pulley just changes the direction of the force, so the tension on this, we don't know.
I don't know if I like this.
But it's less than 50.
I like the inclined plane ones. I like to see those.
Actually, no, I don't like this.
And we have the same over here, we have the
I don't like
weight force pulling it down. Fg equals m1g equals, we already figured this out, 10 kilograms times 10 meters per second squared. So that's 100 newtons. And we know the normal force is still going to be 100 newtons just like before.
So it'd be 50 minus 40.
Okay, but now we know that the sliding friction that's happening right in here is kinetic because we established it's going to slide. So we can calculate that sliding friction force. That's going to be mu sub k times the normal force. Mr. Hannock actually has some students who are Greek heritage, and they know the language, and they said that the Greek symbol that we call mu isn't actually pronounced mu in the Greek language. It's pronounced me. But everyone in the United States, it's commonly called mu.
My girlfriend's Greek.
Interesting.
Why?
I don't know.
Alexa will be back. She's Greek.
FFK equals mu sub k, which is 0.20 times the normal force, 100 newtons.
20.
So we now know that this force here is 20 newtons.
So it's T minus 20 newtons.
So we essentially have two unknowns. We're interested in getting the acceleration, but we also could find the tension force as well. And since we have two unknowns, guess how many equations we're going to need? Two equations. So if we go to our M1, this object over here, we know M1 is 10 kilograms. We don't know the acceleration. And what's going to be an expression for the net force for this guy right here? We know that the weight force and the normal force, they cancel each other out, but we're left with the tension force and the force of kinetic friction.
T minus FFK.
So
So
T
50 minus 1.
minus FFK. And we know what FFK is, so this is going to be T minus 20 newtons equals 10 kilograms times A.
But we also know what T is.
No, we don't.
We do not know what T is. All we know is that it's less than 50
Why do you know that?
now that it's going. Because if this object stayed, then what would T be?
Oh, right.
50. But it's not staying, it's accelerating down. So we know T is less than 50, but we don't know what it is though. So we have two unknowns, can't just solve it there. We're gonna have to look at the other object, this object over here.
No. What did you
No,
say?
the tension's still there. No, the tension's still there because it has to pull it down.
It's still there.
I'm going with
Tension force is still there.
perception.
So let's take a look at the other object, apply apply law number 2 from a man named Ton to the other object. The other object is 5 kilograms times acceleration. But what is the expression for the net force for this object?
F sub G minus T.
F sub G minus T.
Why would it be F sub G minus T? Why would it be T minus T?
We know that it's going to be accelerating down. So which is going to be bigger, FG down or T up?
Oh, down.
FG down.
Yeah, but I also have a question. If MG1 is moving that way, MG2 is moving down.
M1 is going to be moving to the right. Its weight force is pulling it down, but the normal force underneath is holding it up, so it's not moving in the vertical direction here.
Because tension's still greater.
But tension's going to be greater, so that's why it's going to end up going
I was thinking
that way.
the opposite. I was thinking FK is greater.
Right. The friction force is never greater than the applied force. The friction force isn't going to make it go in the opposite direction.
That would be so cool.
Okay, so what is this Fg right here? Well, that's that 50 newtons. So it's 50 newtons minus T equals 5 kilograms times A. There is my other relationship for this object right here. And again, we don't know what T is, nor do we know what A. So we have two equations, two unknowns.
System equation, baby.
Whoa.
Mrs. Sosinski,
Yeah.
when you do the solving for the two equations, can you do it without units? Just so you can
Yes,
figure
yes, 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 yes. Alright, so I'm going to move that over there. There's one equation.
Wow, you're getting familiar with this, huh?
Alright, thank you, thank you. Alright, so those are our two equations. I just copied them from the last page. These two equations right here.
Workings of a master teacher.
Alright, thank you. So, there's many different ways. You could solve both of them for T, set the expressions equal to each other. You could do a substitution. I personally like the adding the equations together. Because if you add the equations together, what's going to happen on the left-hand side?
T's cancel
The
out.
T's are going to cancel out. I'll write the whole thing out. Normally you wouldn't, but I'll say 50 newtons minus T plus T minus 20 newtons. That's adding the two left-hand sides. Equals 5 kilograms times A plus 10 kilograms times A. And these T's are going to cancel out. 50 minus 20 is 30. 5A plus 10A is 15A.
this one and that
Oh,
one.
never mind. I gotta take this away here.
But on top of the gravity going
Why
on
do you
that
have to take
side.
that away?
Cause I'm setting up a different problem.
Which is more powerful, the
Wait, so
gravitational force,
is
which is
everything else okay?
parallel,
Is that
or the friction force?
Angle.
Which is
You're too smart.
sorry about that one. Me and John are having a like conversation about this problem all the time. Well, meantime I'm trying to draw it, which I can't draw for my life.
I can.
Nicole's downfall. Yeah, I know my downfall is I can't draw anything. It's kind of sad. My dad laughs at my drawing.
You seem like somebody who would draw stick figures. Somebody who would draw stick figures.
Meehan's getting a tattoo. Meehan, I don't know what your name.
There's static friction and there's gravity.
Well, we're not sure if it's static friction or not. We don't know the mass
I
of
know,
that,
I know.
so we don't know which way it's gonna go. Gravity only matters about the weight.
I know what I'm saying is that
Because if
there's
M2 is
friction.
heavy enough, it will just pull M1 up. But
I
if
know, I'm
M1
saying
is heavy
that.
enough, it will.
Okay, we are told that M2 is heavy enough
Okay.
and it pulls M1 up the ramp. But it happens to be just the right amount of mass that it pulls M1 up at a constant velocity.
Wow, what a coincidence.
It doesn't make it speed up nor slow down.
Wow.
So what we need to determine is how much mass would it take to pull M1 up at a constant velocity?
Are we gonna have to find like where? What's the mass where like neither of them move
Yeah,
too?
because the equation.
No,
'Cause that would be
it's
tricky.
already established that it is moving.
Okay.
So now we
It already has budged. It's already sliding up the ramp. All we need to do is figure out how much mass would M2 be.
This is crazy.
Yes.
If you had an angle in a problem like this.
Oh, we need the angle here.
Yeah.
Thank you. We
What
need
if
the
you
angle.
need a
Can
tiny
you use
angle?
isn't mu of k tan of theta?
If it's
Only if it's one mass all by itself sliding down the ramp at a constant velocity.
Oh, okay.
Not in this case.
Okay.
All right. So we're a little short on time. So see if you can follow me.
We have a double say, right?
No.
Alright,
Here
so
we go.
why don't we do the
Let's
problem?
go, Mr. Slade.
Here we go. Are you ready?
Let's go.
Okay, so we have this 10 kilograms right here, so we know that the total weight force right there is going to be M1 times G, which is going to be 10 kilograms times 10 meters per second squared, so it's going to be 100 newtons.
Okay.
Now, that weight force can be broken down into parts. Part of it is going to pull the object down the ramp this way, FG parallel. Part of that weight force is going to squeeze it in this way, FG perpendicular. We know that FG parallel is equal to the whole weight times sine of 30. So that's going to be equal to 100 newtons times the sine of 30. Sine of 30 is a half, so that's 50 newtons. So FG parallel
5 newtons, right?
is 50 newtons.
5, right?
FG perpendicular, on the other hand, is equal to the whole weight times the cosine of 30. Cos keeps it close. So that's going to be 100 newtons times cosine of 30, which is 0.87. So that's going to be 87 newtons. So FG perpendicular is equal to the whole weight
And that's the normal force also.
Therefore, the normal force is also equal to 87 newtons.
Okay, so
Now, there is going to be a tension force pulling the object up the ramp. We don't know what that is quite yet. But there's also a sliding friction force acting between the bottom of the box and the surface, and that's different than FG parallel.
It's FFK.
That's FFK. there's going to be an FFK. And how do we know it's acting down?
Because the box is being pulled up.
Because the box is being pulled up. So since we know the motion is going up that way, the FFK is going down this way. And we can calculate that FFK. FFK is equal to mu sub k times the normal force. FFK is equal to 0.10 times the normal force, 87 newtons. So that's going to be 8.7 newtons. So this is equal to 8.7 newtons. So if we apply Newton's second law to this object right here, we know that the net force is equal to m1 times the acceleration. Let's just finish this. We can do it.
Yeah, we got this.
What's F net? Well, F net is going to be equal to T pulling it up minus FG parallel holding it back minus
FFK.
FFK, and that's going to equal M1, which is 10 kilograms. But since we know it's going up with a constant velocity,
A equals 1.
A is 0.
Or A is 1.
A zero,
Oh,
constant
zero.
velocity, zero acceleration.
Okay.
Oh yeah,
So you
because
spent the whole
it's
place
right.
So
it's
we
only-
know that
It's all
T
equal to 0.
minus
That makes sense.
FG parallel minus FFK is equal to 0. And we can bring those minus ones over to the other side. So we know T equals FG parallel plus FFK. And we didn't really have to go through Newton's second law to figure that out. We know that if this box right here is sliding up the ramp at a constant velocity, how is the magnitude of T going to compare to the magnitude of FG parallel and FFK? It's going to be their sum. So what does T end up equaling? FG parallel is,
58.7. It's 50 plus 8.
oh, so FG parallel is 50 newtons. FFK is 8.7 newtons. So what's T? 58.7 newtons. So now we know that that T right there is 58.7 newtons. So therefore, coming over to the other object, that T going up has to be 58.7 newtons, yes? But since it's going down at a constant velocity, what is the FG over here going to have to equal? Well, it is going to have to equal M2G, but since
100 newtons.
since
Oh,
it's
no, no,
moving
no.
downward, folks, with a constant velocity,
Has to be 50.
0 because
how
it's
does this FG compare to that T?
It's great. FG minus 58.
It's the same. It's 58.7.
It's the same because the force down has to be equal to the force up. That's why it's moving down at a constant velocity.
And you divide
Oh,
that by 10. And then you divide by
Constant velocity, right? And then you can divide this. M2 times 10 meters per second squared equals 58.7 newtons. So what does M2 equal? 5.87 kilograms. But bam! Hold on, hold on, hold on.
Oh boy. Chris left
Take
already.
the copy of your take-home quiz.
I'll give this to Chris. He has to
You
get
ran out.
He took a hike.